So the other method for evaluating residues of simple poles is the following. This method is generally the fastest, and it can be extremely fast. Basically, we can use it if there's some way to write the function we want to find the residue of phi in the form p over q, where importantly p at z0 is not allowed to be 0, and since it's a simple pole, that means q itself at z0 must be 0. So the residue is given simply by p at z0 divided by q dashed, the derivative of q at z0. So why does this work? Well, in the sort of more direct method, we came up with a formula for the residue. I write the residue as alternately b1 or res. So we said that the residue is the limit as z tends to z0 of z minus z0 times phi. Now we're writing phi as p times q. So basically we've got z minus z0 times p divided by q. Now this is 0 when z is z0, and this is also necessarily 0. So we've got 0 divided by 0. So we use L'Hopital's rule. So if we apply L'Hopital's rule, we take the derivative of the top. So what happens if we differentiate that? Well, we get p. So differentiate this, use the product rule. So we differentiate this and we get p of z0 plus z minus z0 times p dashed, and then we've got on the bottom we just differentiate this, and in all cases we evaluate well, it's a limit as z tends to z0. So basically this goes because we're making z equal z0. Sorry, I should sort of leave it as z. So then we take the limit as z goes to z0. When that happens, this will go, because it's going to be 0, and we just get left with p of z0 divided by q dashed of z0, which is the thing we're trying to prove.